Hello students, this is Mr. Allen, your geometry teacher. Today we're going to look at section 2.5, which is on reasoning and algebra and geometry. So today's lesson is going to lean heavily on what we did in section 2.4, which covered the law of detachment and the law of syllogism. The objective today is for students to be able to connect reasoning and algebra and geometry. So I think I would highlight the term reasoning. Oops, that's not a highlighter. Let's get a highlighter. There we go. Reasoning. So, and today's going to be more about not getting the answers. It's as much as about explaining the answer. So here are some properties that you're probably at least somewhat familiar with, but let's just go over them very quickly. So the addition property of equality basically says, hey, if you've got A equals B, then you can add C to both sides and that'd be the same. So for example, if I said that, I don't know, X equals 7, then that's the same thing as X plus 1 equals 7 plus 1. Which hopefully you can kind of verify that that's true. Since X is equal to 7, then the left-hand side would be 7 plus 1, which is 8. The right-hand side is 8. The subtraction property of equality allows you to subtract the same amount on both sides without changing the equality. And there's also a multiplication and division property of equalities. You're hopefully familiar with those from Algebra 1. These four here are probably the most used ones in geometry, and I would say that these three here are the ones that are typically the most forgotten. This reflexive property just says, and I know this sounds ridiculous, it just basically says that 7 is equal to 7. The symmetric property says that if 7 is equal to A, then A is equal to 7. So in other words, symmetry means you can just switch those two guys around. The transitive property kind of connects two statements together. So it's kind of, this is kind of like the law of syllogism. So it says if A is equal to B, and B is equal to C, then A is equal to C. So for example, if X is equal to 2 and 2 is equal to Y, then X is equal to Y. And finally, the substitution property, which basically says if A is equal to B, you can replace B anywhere there's an A. So let's see if we can use those properties to do this particular example. It says find the solution to the equation. And then it says explain each step. So if you were going to find, you might be able to just look at this right now and guess what the answer is. But let's say you did it. And if your algebra teacher were here, they would probably tell you to minus 1 on both sides. So that'd give you what? 2x equals what, 4. And then they'd say, okay, divide both sides by 2. And so then they'd say x is equal to 2. And so here's your answer. So here's kind of the gist of where we're going with this. That would have been sufficient in your algebra class, but now you have to give a reason. So to go from here to here, what did we do? Well, we used the subtraction property of equality. Okay. To go from here to here, what did we do? Well, we used the division property of equality. And that's it. So that is connecting reasoning to algebra and geometry. So I am connecting the reasons for the steps. Now this isn't a big thing, but it does require that whoever's doing the work understand what each step means. And I would argue that if you don't understand what each step means, then you probably don't have a deep enough understanding of what those steps are. One more property here before we look at some other things is the distributive property, which I'm assuming you're familiar with. I'm not going to read it to you. I'll just give you an example. If I had the expression 2 quantity x plus 3, and I wanted to quote unquote simplify this, this would be you take the 2 times the x and the 2 times the 3, and you'd get 2x plus 6. I'm sure you're familiar with it. In fact, we can actually do it the other way when we talk about factoring. It should be noted that the distributive property applies to both to addition and to subtraction. Okay, so now these are some key congruence properties. You'll notice that these properties look very similar to some of those equality properties that I listed earlier, but notice that all of these statements have that fancy equal sign with a tilde on the top. That means congruent. So when I see, for example, this statement right here, it's saying that segment AB is congruent to segment AB. Okay, that makes sense. And angle A is congruent to angle A. That makes sense. So that's the reflexive property. The symmetric property, if segment AB is congruent to segment CD, then segment CD is congruent to segment AB. So they just switch those around. And then, of course, the transitive property, if angle A is congruent to angle B and angle B is congruent to angle C, then angle A is congruent to angle C. So notice how it connected the A and the C together. That's the transitive property. So not only do those properties hold for equality, they hold for congruence. So this section is basically the foundation of this thing called proof, which is something we're going to talk a lot about this year. And what is a proof? A proof is just a convincing argument that uses deductive reasoning. Remember, we talked about inductive reasoning versus deductive reasoning. Inductive reasoning is when you just use patterns. Deductive reasoning is when you're using things like definitions, theorems, given information. I guess another one I could add in here is axioms, things that we assume true, postulates. That might be another one to put in here. A proof shows that a conjecture is true using only logical reasons. In other words, we don't just say because, we give the reasons why. The foundation for proofs are the laws of detachment and syllogism, which I mentioned at the very beginning of the presentation. So let's go ahead and look at a kind of a, it looks overwhelming, but this is kind of an easier proof. And the reason it's an easier proof, this is an example of what we call a two-column proof. You probably can guess why it's called a two-column proof, because it has one column and it has a second column. It's a two-column proof. And in the left-hand side column, we have what we call statements, and in the right-hand side, we have reasons. So over here's kind of the work on the left, and then the reasons are on the right. So here's what the problem says. It says, given that C, there's C, given that point C is the midpoint of AD, we want to prove that X is equal to 6. So back in chapter 1, you would have done this problem. You would have just found X is 6, and you would have said, that's it, I'm done. Now you're still going to find that it's 6, but you actually have to prove it. So I've already got the proof pretty much filled out, but there's some missing things, and I'm just going to go ahead and fill these in. And I'm going to go ahead and do this kind of straightforward, and I'll try to explain my thinking. So question 1, or statement 1, I'm sorry, is C is the midpoint of AD. Well, how do we know that that statement's true? Well, we know it's true because it was given. So the very first thing in most proofs you want to do is just look at what is given. And the only thing that's given in this particular problem is that C is the midpoint of AD. So that's easy. That's given. 2, why is segment AC congruent to segment CD? Why is this segment congruent to this segment? Well, C is the midpoint. That's the definition of a midpoint. That's literally the definition of a midpoint. So that's the reason we define a midpoint in that way. Why is AC equal to CD? Now, what happened from here to here is we went from a congruent statement to an equality statement. Well, if segment AC is congruent to CD, then AC has to be equal to CD. That's because congruent segments have equal length. You could also write there that another correct answer would be to say definition of congruent segments. Number 4, 4x plus 2x plus 12. So they went from this step to this step. Oh, well look, up here's AC. What's the length of AC? It's 4x. Up here's CD. What's the length of CD? That's 2x. So that's the substitution property of equality. This is the substitution property of equality. Now the next one, I give you the answer for the reason, but not the statement. It says subtraction property of equality. So we must have subtracted something on both sides. Oh, I bet we subtracted 2x on both sides. So 4x minus 2x would be 2x. And so that's 12. And last but not least, how do we go from 2x equals 12 to just x equals 6? Well, that's going to be the division property of equality. And that will complete our proof. So that is an example of a proof. Now, granted, we didn't do this one from scratch. I basically just filled in the blanks, and this is going to be something that we'll do often in the class. It's actually pretty hard to write these from scratch. We'll try to get to some basic ones, but we won't do any really difficult, super high number level of steps. Okay, so this one's going to be a little bit more involved. This says, what is the value of x, and complete the proof. So they give us a picture here. Looks like we got a straight angle AOC. Okay, so we're trying to find x. What do we call this angle and this angle? They have a special name. That's going to be the key to this problem. So let's go ahead and complete a proof on this. And what you might want to do before you do a proof is actually just convince yourself that you can figure out what x is. And once you figure out what x is, you're probably in a good place. Now, once again here, this time I've already done the statements, and we're just going to provide the reasons. So why is angle AOM and angle MOC supplementary? Oh, I know why. That's that's the definition of a linear pair. Let's not put it that way. Let me write that a slightly different way. Oops. Let's erase. Okay, let's try that again. I'm going to say that a linear pair forms supplementary angles. I'm running out of room there. Linear pair forms supplementary angles. That's what they are, right? This is a linear pair, therefore it forms supplementary angles. Statement 2, so that was statement 1. Statement 2, why is the measure of angle AOM plus the measure of angle MOC 180? Well, because that's the definition of supplementary angles. Supplementary angles add up to 180 degrees. Now, the measure of angle AOM, that's this guy. What's its measure? It's 2x plus 30. And then angle MOC, what's its measure? Well, that's this. So that's just the substitution property. The substitution property of equality. So here, what we're saying is, we've got the measure of angle AOM, which is 2x plus 30, and we've got the measure of angle MOC, which is x. So we can just substitute those in. That's given information in our diagram. So the next step, it looks like we've combined the 2x and the x. So that's going to be, this is actually kind of a trick one. You want to write the addition property of equality, but we're actually not adding both things to both sides. So what I would just say is by closure. If you don't like that, closure. You could write distributive property here too. You write it that way. That's probably a better way of writing it. The distributive property. In fact, that's probably the better answer. Don't worry about closure. Closure, we haven't even really talked about that. So we'll just call it the distributive property because 2x plus x is 3x. That's the distributive property. And now we're going to do somehow that 30 went away. Oh, okay, I see. This one is the subtraction property of equality. We subtracted 30 on both sides. And then, of course, division property of equality. And the reason I know it's the division property of equality is because if you divide both sides by 30, you'll get x on the left and 50 on the right. So here is the solution. Here's what x is. And now we've got our proof and our statements 3, 4, 5, and 6. So linear pariform supplementary angles, definition of supplementary angles, substitution property of equality, distributive property, subtraction property, and division property. All right, so I'm going to end it here with this. This will be our last example for the day. So I started with an algebra one, then we did one involving segments. We just did one with angles. We're going to do one more here with angles. Now this one here, what I'm going to recommend that you do is you to stop this and see if you can complete it yourself. So we've got this diagram. I'll move this video a little bit so you can see it better. The only thing that we're given is that the measure of angle one, the measure of angle one is equal to the measure of angle 3. We're supposed to prove that angle AEC, that's this guy here, and angle DEB, that's this guy here, are equal in measure. So I would pause it here and then resume it after you think. And I've already got the proof kind of laid out here. You have to do it completely from scratch. So the first thing is given. We talked about that. That's an easy one. But now you've got to go from there. Okay. All right. So here is my completed proof, the way that I did it. So it says that the measure of angle 1 equals the measure of angle 3. Well, that was already given to us, right? That was given. Again, if we go back and look at our previous slide, I gave you that one. And I filled in all the statements. Now, here's that one I said that's kind of weird, but it's actually super easy. The measure of angle 2, that's this guy here, is equal to the measure of angle 2. That's the reflexive property of equality. Reflexive property of equality. So now looky here. So look what has happened here in statement 3. Statement 3 kind of looks like statement 1, but they've added the measure of angle 2 to both. Oh, they've added the same thing on both sides. So that's going to be the addition property of equality. The addition property of equality says that you can have the same amount on both sides of the equation. All right, so number 4 now has 2 statements. Now you can actually do this. Since these 2 statements are using the same reason, you can actually combine them on both. Now I'm going to erase what I have up here for a second. Here's what step 4 says. Step 4 says that the measure of angle 1 plus the measure of angle 2, that's this guy right here, equals the measure of angle AEC. That's got that guy there. Let me make 2 marks there. Why are those 2 angles added together? Their measures equal to angle AEC. That is something called angle addition postulate. This goes back to chapter 1. This is one of the things you're going to find in this class. You have to know your stuff, or you need to have a reference sheet close by so you can remember it. Angle addition postulate says if you take angle A plus angle 1 plus angle 2, which are adjacent angles, then they'll give you the whole angle. You'll notice that the second statement in number 4, measure of angle 3 plus measure of angle 2 equals angle DEB. That's this angle. That's the exact same reason. So that's why we were allowed to use 2 statements in that one step, if you will. So angle 5, or number 5, the measure of angle AEC equals measure of angle DEB. Well, here's angle AEC, and here's angle DEB. How can I say they're equal? Oh, I see. Step 3, we said that the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3 plus the measure of angle 2. That's what step 3 says. So this is just the substitution property of equality. And that will complete our proof because that's what we were asked to prove. I've just proved that angle AEC is equal to the measure of angle DEB. All right, that will end the presentation.